So, a very good morning to all, ladies and gentlemen. Once again, a very warm welcome to the 14th edition of the National Additive Manufacturing Innovation Cluster Global Additive Manufacturing Summit. Can we have a round of applause, please? So today is the second day of our conference, and we welcome all of you for joining us here. Just in case right now is your very first time joining us, this is held in conjunction with the Industrial Transformation Asia Pacific. And GAMS is Singapore's flagship in-person business event for additive manufacturing, or AM in short. Now, we're very happy to have gathered global thought leaders, entrepreneurs, as well as leading AM application experts joining us here today, especially to those of you who have especially flown in, which truly appreciate that. My name is Karen. It's a pleasure here to be your MC for today. Now, this year, we celebrate the theme, Unlocking Agility and Skill with Digitalization and Additive Manufacturing. So in particular, we will be finding out more about how additive manufacturing and digital technologies are transforming industries, enabling scalable production and driving circular manufacturing. Now, do note that your event pass will grant you access to the Industrial Transformation Asia Pacific, otherwise known as ITAP trade show, located at Level 1, Hall 3 and 4. So feel free to explore it later on. And of course, we will be taking photos and videos during this event. Now, let us move on to our very first speaker for today, shall we? He is the inventor of the first ever atomic layer advanced manufacturing technology, enabling atomic precision development of materials, devices, and microsystems. Could you please put your hands together to welcome Dr. Maxim Plaktoniuk, founder and Chief Executive Officer of Atlas 3D. A round of applause, please.
Good morning. It's a pleasure to be here with you, and I welcome you all here. It's a great event, and I'm very proud to be. I would like to thank to Cho Sing for inviting and giving the opportunity to be in front of you. I'm a CEO and founder of Atlas 3D. My name is Maxim Plaktoniuk, and I want to talk with you about a new things, a new category that you never met before. So in Atlas 3D, we developed a technology that can revolutionize what we do today. As we all know, advanced additive manufacturing changes the world how we see and how we saw it before. However, we didn't touch how we can change the world with atomic level. And this is what I want to talk today. So what we do, we develop new materials with atomic precision by discovering material libraries. We print materials atom by atom, and not only this, we make micro-nano devices at the same spot with the same tools. Why we need to do this? So our civilization is defined by materials. So we started from Stone Age, Iron Age. Now we live in Silicon Age and moving to AI Age. And for AI Age, we need new materials, more the better. And this is also definition of the new inventions. So how we imagine our future? We imagine our future by defining the new materials. So the new materials that we have today, they're quite limited. However, they define what we can invent today, tomorrow. So from clean energy to quantum computers to biotech and semiconductors. And with AI era, we can make this absolutely different. AI can enable creation of new materials at a speed of light. We didn't do this before. So far, we have been spending 90% of our effort on inventing materials, and they were staying in the labs and didn't leave this. Today, largest companies trying to find new materials and speed up this process. There are geopolitical tensions in order to control materials, from lithium to semiconductors and more. We need to find the new ways how we can make them. With AI initiatives, there are like from NVIDIA and Google and others, they are looking how AI can help. However, when we look on the method how we invent materials so far, it's about 10 to 20 years to bring new material into the applications and industry. So where we stuck? We stuck at every spot, at every point of the process, from how we conceptualize material, how we design the material, how we synthesize material. It all takes few years to make it, until we make the library only the library, not even the solution that we need for the applications. So what is our solution to this problem? With AI companies that exist today that heavily supported, this is the only one piece of the solution. We can invent a lot of libraries. Google itself, with their DeepMind, it generated more than 2 million materials, but where do they stay? They don't move anywhere. They all generated, but they are not synthesized. How are we going to synthesize them? So we in Atlant invented the platform, the technology that can synthesize materials, not one, not two materials, but can synthesize whole libraries. More than 450 different materials, from semiconductor to aerospace to biomedical and more than this. And our core for this invention, we call it DALP technology. It's a hardware platform that enables synthesis, in situ metrology, data processing, and creating libraries. And more than this, we create also prototype of devices that one could use. You might think it's impossible. It is possible, and I'll show you how we do this. So we use our proprietary technology. It's a micro-nozzle technology. It's a microfluidic device that allows to deliver gas flows to the specific spot and synthesize material at a spot with atomic precision, one atomic layer at a time. So how it works, we have different flows that come into the surface from one reactant and a second. So we create on a surface chemical reaction with one atomic layer at a time. More important, this process you can control digitally as any other additive manufacturing technology, but here you can mix materials. So in reality, you don't synthesize one material, you can synthesize whole libraries of materials. 2 material combination, 3, 4, 5. This was impossible until today. This process is obviously digital, where you can design the material, submit the file similar like in 3D printing, and since we also engage in semiconductors, so we use semiconductor file standards, and simulate how the printed would go, how much time precisely it will spend. And then you get the device as you wish, not only device, materials and devices. This is how in reality happens. You select the material you want from 22 categories, either for biomedical or for sensors, what you want to develop. You develop the library by testing many simple material tests. It happens in hours, not in years. And then when you choose the specific parameter of the material, you integrate into devices and you see how actually it's functioning. What materials and devices in general you can make? Materials for power electronics, for RF, for advanced packaging, for protective aesthetic coatings, to logic and memory, to photonics and the optics, energy application and catalysis, sensors, environment applications, quantum materials and frontier applications like neuromorphic or superconductors, biomedical interfaces. And this is only the overview. There could be other new material groups that we didn't spot yet. What is the benefit when we look on the bigger picture? So we reduce the development towards the conventional method by 100 to 1,000 times faster. From 10, 20 years to only weeks or months to develop the material and test them as the devices. It's exponential reduction of the time and capabilities and enhancing capabilities that were never before. This is one of the examples. One of the customers came to us asking to develop neuromorphic system. And you always start with the material development. So we developed the material library. This is a gradient of one of the materials that we developed. We started from few nanometers to 100 nanometers. We don't even need to make simple or separate samples. We just grow gradient. And with that gradient, we test the thickness, the properties like electrical, optical properties, and then when we find the spot we need, we integrate immediately into the working devices. Now it's moving into real industrial application. And for this, we spent only few months with an engineer, not even PhD level expert. It was the engineer working with this and developing with the partners. This is a second example for optics. The optical filter where you need to test and create heterojunctions, optical heterojunctions, and define also the gradients and also how to combine refractive index. So we developed the material only in few weeks and then completely integrated in devices in a few hours and then tested, of course. So how we all make this? We make it with the different machines. Our machine is based on the same principle, on DALP technology. What is common between all these machines? That you have the same print head. What this means? That you can scale from small machine, like for zero gravity, for space, down to the large machine. And if you invent the process on one machine smaller, you can easily transfer to another one because it's a digital process. You only need to know what nozzle you use, what device actually would be printing, because this is the device that defines how you do the work. In other technologies, you need to really know the chamber, vacuum, and so on. Here, you don't need to do this. You only need to know what material and what nozzle you use, and then you transfer, and it's working. So right now, we are releasing the 8-inch tool that would work specifically for semiconductor applications and materials. And we now working on a cluster that would combine different technologies together. So we integrate in our technology with industrial standards today. We now, more than this, looking for the partners who can help us develop the whole cluster for industrial integration. We're already working with US and potentially would find a new partner soon, here as well in Singapore, both industrial and research. And we're looking who else can join us for this material revolution. It could be you. So come and we can talk after. So what the cluster can be. So from automatic sample handling with like multi-wafers to processing to in-situ metrology, where this can happen very fast, where human interaction would be to give the task as that's it. Everything else, the data set, material, libraries, would be automatically generated, tested, and then provided you as a report. So what is the opportunity behind when we implement all this? Guys, we are changing the trillion markets. And I think it's underestimated what I'm showing you here. Because semiconductor industry, particularly since I'm coming from there, it didn't see a revolution for 70 years. We still operate on principles that were defined in 60s or even earlier. While we bring additive manufacturing today to print concrete buildings, where we print metal structures, semiconductor industry way behind. We can't even invent new materials there. Imagine what we need to do to change and how much it will influence on all of us. How fast we can make microchips, quantum computers, superconductors. We will create our future not in decades, but in years or less than this. So how we operate? So Our strategy is not to only provide the equipment, we define in software, we build in the platform. We build materials, libraries, processes, integrating them into the customer applications, and we look in and integrating strategic partners. All this we call the ecosystem. We developing the ecosystems. Ecosystem that will change industries. We're looking for you to be the partner in this ecosystem, local here in Singapore or in New York or in Japan or elsewhere or in Europe. This is what our plan for the next few years. We have already our first ecosystem in Denmark where we are located. We're looking to establish a second ecosystem here in Singapore. That's why I'm actually here today with you. And we want to enable Singapore particularly to be the AI material-enabled country, creating the future that with the speed of light that no one even thought about. Creating not only materials but applications that only could be possible when you bring the innovation with the cutting edge. So what would be here in Singapore? We call it A Hub, the A Hub that would create the future for Singapore, from material discovery, functional validation, to integration and scaling in industries. So accelerated innovation enables sovereignty that was not possible by expanding new capabilities. Scale globally, because if you invent new libraries of materials, you can create and attract new partners here. You already have a very powerful partners. Imagine with the space and territory you have here, with innovation on materials, how many new partners can come and actually settle here because you can bring new materials in years instead of decades. It will attract more strong partners, global partners, to work in Singapore. And just didn't say that this will create a huge sustainability impact because we are additive. We are by default digital technology. We don't need multiple processes to operate. So all this will create a huge value, not only for Singapore, but for the global economy, for enabling new applications and new innovation. I just want to show you one thing, what our technology can do behind this. This was, I don't know if this is visible, this was our first print of digital image, Abraham Lincoln. He's looking from the past on us to see how responsibly we can create the future. We print atom by atoms. We creating something that was not possible until today. And on this, I want to say the last phrase. AI designs the materials. It can create millions of materials. Atlant 3D can create them, atom by atom. Thank you.
Thank you very much, Dr. Maxim. So, of course, everybody, we hope you've enjoyed that. Moving on, while additive manufacturing has demonstrated immense potential in prototyping and customized production, scaling it for high-volume industrial use remains a complex challenge here today, which is why I would like to examine what exactly does it take to move additive manufacturing from cutting-edge innovation to widespread industrial adoption, spotlighting real-world case studies across sectors and highlighting the potential challenges. Let us welcome Mr. Matthias Schmidtler, Managing Partner, AM Power. A round of applause, please.
Yeah, thank you very much. It's a pleasure to be here. Thanks for the invitation. My name is Matthias Schmidtler. I'm partner at Empower, one of the consultancies in the additive manufacturing world. We're based in Hamburg in Germany. Yeah, and it's my pleasure to introduce the next session that is about bridging the gap between innovation and industrialization. I remember 2016, I think it was, when the first Formnext started in Frankfurt. I was back then with the Laser Centrum North, that is one of the very early research institutes in Hamburg that used laser-based additive manufacturing technologies. That was my starting point with additive manufacturing at this institute, and the Formnext 2016 was the first pure 3D printing exhibition, the first big exhibition really dedicated to additive manufacturing, I think even globally probably. And it was a time where when you were at the booth presenting 3D printing technologies, there were not so many companies back then. There was a couple of service providers, a couple of machine OEMs like SLM, EOS back in the days. And it was still a time when every second, even more than every second person that approached you at the booth was looking at the parts you exhibited there, telling you like, is that metal? Can you actually print metal? It's amazing. Everyone was excited, didn't really believe it. First questions always dealing with, is that actually dense? Is that titanium even, stainless? What can you print? What can you do? It was a time just 9 years ago now, yeah, 2016, about 9 years ago, when many companies who today heavily industrialized additive already, but back then many people came to the booths asking about what is 3D printing and what can it do. And today, fast forward, we have a completely different situation. We have many of the leading companies in high-end, let's say high-end manufacturing, in aerospace, energy, medical. Those companies, most of them, I would almost say all of them, adopted 3D printing to a certain degree. But the question is, did they industrialize it really? And yesterday we talked a lot about innovation. Just now we heard a lot about innovation. Now you can print atoms, not even metal or plastic or concrete now on an atomized base. But let's move forward from innovation to industrialization. And last year at Formnext, there was an interesting presentation at a Nikon event they held there. Someone from Rolls-Royce, I think it was, said, industrialization means additive needs to become boring. Because when you want to produce a part over and over again to the same quality, to a certain level of reliability of a product that you guarantee certain functionality for as a company, since it's flying in the air, it's being built in an energy turbine, or it's being operated into the human body, additive needs to become boring. And if you look at a lot of additive manufacturing facilities nowadays in medical OEMs like, I don't know, Stryker or Siemens Energy in the energy route, those manufacturing sites do look boring to a certain extent because there's not much innovation going on there anymore. It's about reliability, it's about quality, and that's what industrialization is unfortunately about, transforming the exciting part of innovation into manufacturing actual products. And now this next session is about exactly that. We have 4 very esteemed speakers representing 4 companies that provide solutions for industrial additive manufacturing. I think, thinking of it, all 4 of them, I would say, are focusing their whole ecosystem and value proposition on providing solutions for industrialized additive manufacturing. With Alex from HP providing that in the metals, and first of all in the polymers, and then second of all in the metals area in a more innovative process. With BLT representing the metal AAM base, especially in China. With 3T focusing on providing services, explicitly in Europe and the US. And with Nikon SLM, who provide machines in powder bed fusion, focused on industrializing additive manufacturing. That's what it's about now for the next 1.5 hours, I think, 2 hours. So I'm very happy to have that little upfront speech to introduce that topic to you all. And I hope you have a great session now about industrializing additive manufacturing. Thank you very much.
Thank you very much, Matthias. Alrighty, now the next individual who's about to take the stage in just a while, he is equipped with more than 15 years of experience in various roles at HP across various business units. And together with this extensive industry experience and a deep understanding of the additive manufacturing market, he's definitely a key player in advancing strategic priorities to unlock new opportunities and accelerate the mass adoption of advanced manufacturing. Please put your hands together to welcome Mr. Alex Monino, Senior Vice President and General Manager, HP Additive Manufacturing Solutions. A round of applause, please.
Thank you very much. Good morning. Okay, so it's a pleasure to be here in Singapore. Thanks a lot to Namik for the invitation. Singapore, I'm Alex Monino. I manage basically the 3D printing business at HP on a global basis. I'm one of the founders. Singapore is one of my favorite cities, and as we've been here interacting through these days, people have been asking me if it was my first time in Singapore, etc. So I've been counting, over the years, and I cannot count the exact number, but I've been in Singapore between 20 and 30 times. So it's to the point that last year I was able to bring my family to Singapore on holidays, and now Singapore is their favorite city. And as I've been sharing pictures with them this week, I've made them very jealous that I'm here and they're not. Okay, so and there is a reason why I've been 20 to 30 times in Singapore. I've been with HP for 28 years, and during that tenure, basically Singapore has had a very big role, and that is why HP is very well rooted in Singapore, okay? This year, we are very proud to celebrate the 55 years of HP in Singapore, and I've been told we're one of the first international companies that got established in the country with a center of excellence. We have thousands of engineers, highly qualified engineers in Singapore that work across the different businesses. We have the headquarters basically for all the APJ region management, but also we have all the engineering resources. As you know, HP is a very big global company where operations are huge, and all those operations in Asia are managed from Singapore. Besides that, we have R&D, high-tech R&D and manufacturing for everything that is our printing inkjet business, which is very high-tech. And going down to 3D, in 3D, we obviously not only have the headquarters for sales and service in Singapore, but we also actually manufacture the printers about 7 minutes drive from here. So all the 3D printers that we sell are manufactured in Singapore because we needed, a very high-tech environment. It's a very high-tech piece of equipment, and we needed a high-tech quality environment above cost in order to have success in the market. So let me give you a little bit of a glimpse of the history of HP in 3D printing. Matthias was talking about the first Formnext in 2016. That's pretty much when we launched the first product. Okay, so we've been in the market for 9 to 10 years, learning a lot. Scaling in this market is never a straight line. Not for us, not for the overall market. It's full of turns and surprises. But it's been a great journey, and we've been really driving the adoption. Since we started this business, our focus was to drive manufacturing transformation. We decided not to play in prototyping, and we decided to just focus on what Matthias was talking about, which is the industrialized 3D printing as a manufacturing technology, both in polymers and in plastics. Our polymers business is much more mature than the plastics than the metals, because we basically started much earlier. And this has been our objective and our strategy since then, to accelerate transformative manufacturing, making additive parts available to everybody, everywhere, okay? And, making that in the current environment on 3D printing, there is a lot of turmoil. There is a lot of companies that are here today, they're not here tomorrow. Our strategy is to be there. You saw the video, many of you, that we presented yesterday in the MOU on the Barcelona facilities that we have, which are the headquarters, together with all the facilities we have in Singapore and in the northwest of the US. And we did that video because when we bring people to Barcelona, we can showcase the amount of innovation, energy, and investment that we're putting into this business. And therefore, the trust of those customers increase. We cannot bring, not all the customers can come to Barcelona. They're all invited, but not all of them can come. So we wanted just to put that piece of video so to give them a glimpse of what is there, to give them confidence that we are a trusted partner in the industry, that we're not here to go away in the next year, we're here to stay, and that we continue investing with energy to drive this transformation, right? And what it drives, whoops, so my screens disappeared here, if you can fix those. So basically we want to help our customers at every stage of the production journey. And what that means is that from the moment they start considering additive, okay, we have a network of service bureaus, okay, that we've been building over the last 10 years, and it's very extensive, so we can have them access. To the moment they decide to insert their first solution, right? We have a portfolio of solutions to help them from the very beginning until they really want to scale in manufacturing. And at that choice, there is customers that they decide to insert their own manufacturing. There is other customers that then basically they decide to go externalize to a contract manufacturer or one of our digital manufacturing network members. And all of that, I'm a firm believer that if something already exists, and somebody has solved a problem, don't reinvent it, don't do it again, don't try to compete. So we are a firm believer of this industry ecosystem to partner with people that has already solved problems, to stitch solutions and put together solutions with customers from different players in the industry, rather than try to reinvent everything again, okay? So if we look at ourselves as an industry, it's obvious that everybody understands that it's a technology that's proven for prototyping, that is proven for final part, but as Matthias said, it's easy to do one final part. The difficult thing to do is to do hundreds of thousands of that part in a repeatable way with the right equipment efficiency, the right yield, and that's called basically manufacturing, right? And that's what we'll basically drive. In order to drive that, we have 3 pillars, and I'm going to go very fast to this and jump into use cases. Number 1 is the use of AI. Right? Downstairs, Namik is showcasing a great agentic AI use case, for machine maintenance. We are having our own, at smaller scale, we're having our own, maximizing the AI tools that are available to us in order to optimize the maintenance, predictability, build management for customers, okay? And that's something that we'll continue using more and more. The second one is TCO and sustainability. To really drive production adoption and manufacturing adoption, we need to make sure that we have competitive costs with other technologies. That is our gateway to entrance. Once you're there, then you can take all of the other advantages of additive manufacturing in terms of geometry, complex geometries, where you produce, etc. Okay, and obviously, as I mentioned, TCO is not only about cost of powder and cost of equipment, is really about your yield, overall equipment efficiencies, and the overall end-to-end manufacturing process. And last but not least, it's about industry partnerships and collaborations, okay, that we unveiled one yesterday here for Asia-Pacific ecosystem. So I want to spend the next few minutes just giving you a glimpse of particular use cases. I'm going to focus on APJ use cases, okay, that are within this region, where we have successful use cases of applications that we've basically moved to production. The first one I want to explain is Soltrix. It's a customer that we have in China. It was one of the first adopters of our metal jet technology. And basically, they're printing hundreds of thousands of parts on a production environment, many of them on the consumer goods space. And they're doing it with industry standard materials and industry standard finishing, okay, which gives them an edge of competition that you don't need to reinvest the ecosystem, you don't need to reinvent the ecosystem or something very particular. And we're seeing that customer really scaling with applications. And then, again, once you have the right cost, you can see some of the parts here with some geometries that would be impossible to do in 3D additive, but some other geometries that you could do in CNC, etc., and just additive makes it a much more efficient process. The other customer jumping countries is in India. It's Indomim. They have facilities both in India and in the US. It's a metal injection molding house. Okay, and the original intent when they took our technology over is to start converting some of the applications that day-to-day do in metal injection molding into additive, okay, as they show runs, complex geometries they cannot make, etc. They realized that actually additive, it's a great technology to do molds, and in particular binder jetting enables them to do molds with conformal cooling channels. Okay, so they do the whole molds with conformal cooling to the point that then they can do much more complex parts in metal injection molding and have much more productivity. So, you know, kind of an unexpected use case from that point of view. I know there is many tooling that is being done in additive, but in this case, the conforming channels is something very unique that I think, you know, will drive more and more adoption. Moving to Australia, you know, this is a medical use case. iOrthotics, they started in Australia and through partnerships, they're operating globally right now. They're printing hundreds of thousands of insoles. You know this application, basically, or polymers application is great. It's one of the leaders for doing this type. And you know, the nice thing about this application is that it's helping to improve the life of many, many people across Asia Pacific and across the globe. So that's another one. The next one I want to mention is Cobra Golf, and this picture is based on based on our metal jet technology. We're printing tens of thousands of golf clubs. These are the patterns that what I'm showing on the picture, and everything that's inside basically is 3D printed. And they're printing tens of thousands of clubs here in Asia Pacific for the global market. But one picture I'm not showing is for those that play golf, you know, you have the putter and then you have the drives. In the middle, you basically have a number of irons, okay, from the wedge to the 5. All those irons on the back, on the high-end, on the mid-range and high-end brands, they have a plastic part, right, that covers, and I don't have a picture for that. We are producing today 1 million of those parts a year in China. So pretty much many of the brands that are selling those are being 3D printed, and they're being 3D printed because it's a complex part, and then they can vary the weights. So, you know, you talk about a production use case, 1 million parts per year. That I call production, okay? So, and that's already being done with additive, with the right quality, with the right yields, okay? I'll be able to share more details over the next few weeks and hopefully some pictures. And then one of the segments that is growing fastest, and this is the one I'm going to share one use case that is not Asia Pacific in particular, is drones, right? In drones, obviously it goes you know, on a different array of segments from commercial, delivery, defense, and even medical. You know, I was at the Veteran Administration Hospital Network a few weeks ago in Seattle, and they're working on a network of drone delivery system interconnecting the different hospitals, making sure they can share, you know, blood samples, etc., medicines and drugs much more efficiently. This particular case is from a customer in South Africa. They are developing a drone. They've developed this drone. It's already operational. Pretty much all the drone is 3D printed, obviously except the motors and the rotors. And the intent is to basically watch out the savanna. Okay, they deploy them in the savanna in Africa, and they're looking for illegal hunters. Okay, and what they're looking is trying to protect the animals, count the animals, and you know, keep the savanna in good condition away from illegal hunters. And actually, they have a social benefit as well. They're transferring the jobs of the illegal hunters. To fly every drone for regulations, you need a pilot. So they're training people that they're trying to make a living from illegal hunting to be a drone pilot to watch the savanna. So they're doing that change. So it's a great use case, great story. And you know, they've helped develop. We have a technology in polymers, and you see some of the pictures here. I'm going to run this video so you can see. There is a light. So you can see we are printing 0.3 millimeter walls with a structure that holds. That allows us to basically reduce 40% of the weight of the drone, of the frame of the drone, compared to carbon fiber. Okay, so That means that with that 40% reduction on the structure, and we can, on the wings, we can reduce about 30% of the weight, you can increase the range of the drone. You can put all that weight that you save on the structure, you can put it back on the batteries, okay? That means that you can fly that drone 30% longer, okay? So we're increasing the range of the drone 30% longer, and we're seeing a lot of growth, basically, on drones based on this technology that we can provide. Okay, so those some of the use cases, and looking forward, and wrapping up. Number one, I think additive manufacturing is no longer a niche. I think we'll see more and more use cases on production, and we'll discuss at length in the panel. Proving itself that we can be in manufacturing, and then to scale it further, I think everybody in this room is a believer of additive manufacturing, otherwise we will not be here, and it's very aware of all the use cases. I think the key is that we continue spreading the word, we continue credibly spreading the word that additive manufacturing is ready for manufacturing, so we have more and more customers that are either unaware or skeptical, basically adopting this technology. And to do that, again, there is nothing better to partner, okay? And this is what we announced yesterday, a partnership with NAMIC and DAOE Technologies to really help drive and scale the adoption of this technology in Southeast Asia. So with this, thank you very much, and I look forward to the panel discussion later. Thank you.
Thank you, Alex. So in just a while, we will be welcoming the next gentleman who has 2 decades of manufacturing expertise spanning aerospace companies. And in fact, he has just spent the last 10 years at the forefront of metal additive manufacturing's evolution from prototype to competitive series production. And he's none other than Mr. Eddie Andrews, Commercial Director of 3D Additive Manufacturing. Let's welcome him. A round of applause, please.
I brought some toys with me. Just following on from what Matthias was saying before, I'm here to represent the boring, but hopefully this won't be boring, so bear with me. The additive manufacturing sector is sitting on a multi-billion-dollar opportunity, but up to 90% of the AM metal contract manufacturers are following the wrong strategy. That sounds a bit dramatic, doesn't it? Okay. But over the next 15 minutes, I want to talk to you what happened when we stopped doing what everyone else was doing and how we transformed 3T from a prototyping business into a production manufacturing company. This is what we see in the industry today. The narrative is all about the focus on the additive process itself. We've heard it here this week a lot already. We focus on bigger machines, more lasers, new alloys, the perfect application. But the real opportunity is under here. It's in vertically integrated capability, the ability to deliver a finished component that competes on cost and on quality. Now, we're here because I believe that Singapore understands this better than most. Your government has been pushing integrated manufacturing and Industry 4.0 for decades. You know that innovation without industrialization is just expensive R&D. This came from a market research paper this year. It says that there are 257 metal AM contract manufacturers globally with just an average revenue of $5.8 million. Think about that for a second. $5.8 million. That's tiny for a capital-intensive manufacturing business. Now imagine this. We wake up tomorrow and all the subsidies that are funding this industry are gone for good. How many of those 257 companies do you think would survive purely on their own commercial strength? In my opinion, I think we're looking at around 10 to 15 companies globally that would survive a 12-month period. And this is the issue that we're facing. We're already starting to see this playing out in parts of Europe already. Matthias mentioned Formnext. It's the biggest show in additive manufacturing in Europe. And this is happening this year. Subsidy programs are starting to wind down. It's already starting to happen to our industry. And here's where this matters to our customers. Imagine you're an aerospace customer. You've got an internal AM capability, and you've been developing AM parts for years. You've fully developed an AM part, you've qualified it internally, and you're ready to launch it into production. And then you go out and scan the supply chain to see what the capability is like. You know that the capacity needed to deliver this program needs 30 printers, 5 CNC machines, a vacuum furnace, 3 wire EDMs, special processes. You know you need a full material test labs and an inspection capability. That's a significant investment for any of those suppliers. Now look at the risk then for the customer. Out of those 257 companies, who's got that available capacity? No one. No one's got that capacity, and they shouldn't have that capacity available, or something would be dramatically wrong. But out of those 257 companies, who's got the financial growth behind them and investment to actually make that level of investment? Very few. And even if I commit as a customer to any one of those 257 companies and they can't perform, they can't deliver, what's my plan B? How much is that plan B going to cost? And how long would it even take to get a plan B? And that's why our customers are perceiving production in AM as too risky right now. Not because the technology isn't good enough, it's because the supply chain isn't mature enough. That's the problem. As an industry, it is our jobs to develop a capability that is production ready, that gives our customers not just a plan B, but a plan A through to Z. Sorry, I've skipped on. So what happens instead, our customers are designing parts with mitigations. They're not committing purely to AM. Their mitigation right now is design parts that can be manufactured another way. There are unicorn applications out there, but they only exist in the OEMs because they're developing them in production in their own internal facilities because they deem the supply chains as too risky. That's why chasing after unicorn applications within the supply chain is not the right time. We all want to get to this top right-hand corner, or at least we should all want to get to this top right-hand corner. Parts that are designed purely for the additive process in high series volume. That's the dream. But there's 2 paths to get there. The first path, no reaction to the unicorn, okay. The first path, and this is where 90% of the companies are, they're still innovating the additive process, and they're chasing these unicorn applications. These are also the voices in the industry that are saying it's not possible to get into production. But path 2, this is where the other 10% are. This is about integrating the supply chain, focusing on the cost and quality of the components needed to get into production. And this is the part of the industry that is quietly just delivering production today. And here's the secret. To get enough customers confident in production, we need enough suppliers that are capable of production. We need to give them the plan A through to Z. 3 years ago, 3T was heading towards that 90%. We were doing what everyone else does in AM. We were trying to be everything to everyone, chasing those unicorn applications that in reality were never going to happen. We were like a McDonald's trying to chase Michelin star orders. We were just busy fools. What did that look like? We had hundreds of customers, RFQs that we couldn't handle. We had no focus. We had a huge sales and engineering team, all to execute very low-value orders. We had over 20 alloys running on our machines. We spent more time cleaning the machines than we did actually running them. Our supply chain was huge. Every week we were sending parts out to have something done. We were just praying for the right quality and the right lead times to come back. But in reality, the cost was killing us. Our cost of quality, our scrap rates were through the roof. Our lead times were crazy and uncontrollable. And our cost base was out of control. We were just having margin on margin on margin. So we made two fundamental changes to our business. Change one, we stopped innovating the additive process and we started integrating the supply chain. And step two, we stopped reacting to every RFQ that came through the door, and we started properly listening to what our customers wanted. And with that, we started tailoring what our services needed to be so that we could deliver on our customer expectations, all internally. Now, this isn't a novel mic drop moment. This is just what mature manufacturing companies have been doing for decades. We integrated the internal value chain into one facility. Now our customers come to one supplier for everything, development all the way through to production. Our lead times improved. Our cost became more competitive. And our cost of quality is now less than 2%, which is comparable to world-class manufacturing metrics. Today, we compete on cost and quality, but the value that we create using this model is answering some of the biggest questions that are being asked within the customer boardrooms today, and I'll go on to that shortly. But last year, this model enabled us to deliver 12,000 high-quality metal components, all to customers in highly regulated industries. And this is where it gets interesting, and I hope Terry Wallers isn't in the audience today, because this is his chart, but he's not on his own with this chart. Because this is the narrative that we see in the industry, and it shows the printing at 60% of the cost of an AM part. 60. Now here's where it gets interesting. What happens with this narrative is quite predictable. Everyone believes that the key to success is to improve the printing process. So what do? We all focus on these guys, and we say innovate the machines. Or reduce the cost of the machine. That would be nice, wouldn't it? Now, I'm not saying that I wouldn't appreciate a cheaper machine. Nikon, BTL, no, BLT, no, cheaper machines. I'm not saying I wouldn't appreciate them. I'm just saying that it's not the only cost that we need to consider when we're trying to drive a route to production. In comparison, this is an actual component that we make for Airbus today. This part's qualified and flying. We make thousands of these parts each year. Do you see the difference? The cost of the AM print is only 20%. Nick from Boeing also said the same thing. That's what he's seeing today. This is reality. 20% of the cost of an AM part is in the print. And that means that 80% of the cost you can go at without even touching the additive process itself. And that's how you get production. This is the data that your customers don't see when you're responding to the RFQs, but it's the data that determines whether or not you're going to get into production. So to summarize this first section into a little bit of a formula, the route to production can be simplified as integrating the internal supply chain needed to create your finished parts. Then listen to what your customers' problems actually are: cost, quality, lead times. And do that, and find the applications that actually make sense for them, not the unicorns. Do that, and you'll achieve production. And then comes the hard work: operational excellence, delivering on commitments, taking cost out systematically. And the more production you get, the more opportunities you'll get to take cost out. It just keeps on getting better and better. This is our actual finance data for the last couple of years since we acquired the business. 3T's transformation took 3 structured years of business change. Our EBIT recovered from minus 30% to plus 8% forecast for this year. Our order book grew from 300,000 pounds to over 11 million. And our quoted pipeline of real opportunities, not speculative, but real opportunities, is now in excess of 50 million pounds. Each year we became less reactive and more proactive, which gave us the visibility to make better decisions and drive customer focus and systematically reduce our costs even more. 2 months ago, we announced the acquisition of 3T by a large Austrian multinational company who are centered around precision manufacturing. This means that 3T isn't just doing this in the UK now. We also have the capability to make a finished component using metal AM in the US, Austria, and the UK. And SBO also have significant manufacturing footprint in Southeast Asia, both in Vietnam and here in Singapore. And it's highly likely that our next big investment in AM will be here in Southeast Asia. Why? Because Singapore understands integrated manufacturing. And all of our customers are proven sectors, all based out here: aerospace, space, defense, semiconductors, oil and gas. It makes sense for us to be in this region. And here's what I believe. If more of us adopt this model and this proven approach of integrating the supply chains, focusing on the finished part, operational excellence, taking cost out systematically, we will grow the industry from 10 to 15 capable suppliers to hundreds. And that will give our customers the risk mitigation that they need to commit to production. And that will be the pivotal moment when the actual growth rates in this industry will far exceed industry charts like this. Everything that I've talked about so far is addressing cost and quality, and that's how you get to production. But the real value that this enables is hardly even spoken about in AM. It's the value that addresses the 2 biggest topics in your customers' boardrooms today: supply chain resilience and decarbonization. A few years ago, I was speaking to an aerospace customer, and he told me something that changed how I think about our value. He said, "We have our own internal factories, and we can drive them to net zero within about 6 to 12 months. That's easy, and that's scope 1 and 2 in the middle. But we have 3,000 suppliers in our supply chain, and that's the scope 3 problem. And we have no idea how to fix it." And that's when this made sense. This business model that we have of integrated supply chains plugged into using renewable energy isn't just a way to compete for the finished part in production. It's our biggest opportunity to act and support our customers with their own net zero commitments. This is an actual use case from Airbus. They did this a decade ago, and it speaks to the material waste in the industry. Now imagine we've got two parts, exactly the same parts in titanium. One part is from AM, and the other part is from billet. Automatically, I've just saved 95% material waste. How? Because this part needs less material, 8 times less material to go into the feedstock to make the additive part. That means that 3 times less mining needs to happen to pull out the same amount of material that I need to create the feedstock. And because of that net shape material, I'm going to create 48 times less material waste in that process. Now, I talked about 3T delivered 12,000 parts last year. By doing AM rather than billet manufacturing, we prevented 48,000 kilos of material waste, and our turnover was 5 million. Imagine how big this industry is going to get and how big that problem is that we're going to be saving. And this example here is one of the best examples of material waste I've seen in additive, and it's an example from ASML's machine. This is a titanium assembly of 2 different additive manufacturing parts. One is from powder bed, which is from 3T, and this is DED from Norse Titanium. The amount of material saved here could fit in a 1 meter cubic box. And there's more benefits. When you integrate the supply chain into one facility, you're significantly reducing the amount of logistics CO2 footprint. And when you're plugging your facilities into renewable energy and you've got the entire value chain in your facilities, you're significantly decarbonizing the end-to-end manufacturing process. Now, this GE example is the only example that's really talked about in additive in terms of its sustainability credentials. And this is the GE nozzle, which I think saved 15% on the fuel burn. And that's using the capabilities that AM has to create parts. And that tends to be the narrative around AM. But there's also the end-of-life waste. We're seeing that the microstructure that we create in these additive parts is lasting longer when compared to castings, which means these parts are lasting 3, 4, 5 times longer in their applications, which means our customers need less parts, and less parts are going to waste. So we're back to where we started, and I think the additive manufacturing really does have a choice. We can continue being the promising technology that just needs 1 more year, 1 more grant, 1 more breakthrough, or we can become the integrated manufacturing solution that stands on its own 2 feet before it's too late and the subsidies go forever. So you'll hear a lot of talks over the next couple of days or the last couple of days. And from me, if you remember one thing from each one of these presentations, that's good going. And from me, I'd like you to remember one thing. When you get back to your factories on Monday, do a deep dive and map the entire cost of an AM part, not just the printing, the entire part. Include everything, all of the manufacturing processes needed after the additive process itself, whether you do them in-house or not. Include the OEE, the scrap rates, the rework cost, absolutely everything that contributes cost in your process. And then ask yourself, am I investing in the 80% or the 20%? And that's where the opportunity is. 3 years ago, 3T was like a McDonald's trying to chase after Michelin-priced orders. Today, we're heading towards our Michelin-star restaurant, which is capable of delivering production and it's profitable to stay in business. This is the model that works, and this is the model that scales. The industry has everything it needs around it to make this a success and turn 10 or 15 suppliers into hundreds of suppliers. And all it takes is a shift in perspective. Thank you.
Thank you very much, Eddie. So, of course, it brings me great joy to welcome our next speaker, who will be taking the stage in just a little while. Now, the next individual is a seasoned professional with over 20 years of experience in advanced manufacturing, and he has also served as an influential leader contributing to the broader adoption of additive manufacturing solutions across the globe in aerospace, power management, and automotive industries. And he's none other than Dr. Barang Puganji, Vice President of Technology, Nikon Advanced Manufacturing Inc. Let's welcome him. A round of applause, everybody.
Thank you. Can you hear me? Okay, very good.
How is it?
Thank you for the introduction. I'd like to thank Namik and Chao Singh for the invitation. I think this is my first time here giving talk as invited speaker. It's a pleasure. Thank you for you guys coming here on Friday morning. I think it just showed that you're really, really interested in additive manufacturing. So before starting, how many of you are from industry? Can you raise your hand? Okay, I think around 30%. How many representing academia? Around 30%. Okay, what about the other 40%? Where are you guys coming from? Government? Maybe very few. Okay, and one more question. How many of you have had a chance to make a part and go through qualification and potentially certification process? Can you raise your hand? Very few. Very good. Okay. Why I ask this question? We're talking today in this session and the panel about accelerating adoption of additive manufacturing. And there are definitely areas that you need to experience making a part to really understand what are the pain points and how we are collectively together going to accelerate the adoption of additive manufacturing. And today, I want to talk about what we are doing in Nikon AM. So most of you probably know the brand Nikon and the logo, and we are a camera company. Yes, we are a camera company, but that's not the only thing that we do. Actually, a third of our company is semiconductor equipment manufacturing, the lithography equipment. Many of the chips, flat panel displays, they basically produce on our equipment. So in a nutshell, Nikon is a company with expertise in optics, optomechatronics, precision manufacturing, and system integration. And if you look at the additive manufacturing machine, especially like laser powder bed fusion, that is our focus. These machines are optical tools and optical devices. They are very precise, making very precise parts. And to the credit of my friend Shane Collins, that some of you may know, he is actually saying that all the machine manufacturers are system integrator. And I totally believe that we are all system integrator. So in that sense, what we are doing in additive manufacturing is pretty much like, rooted in our DNA of being a company with expertise in optics, precision, and system integration. So what is Nikon AM today? We are a global company. Headquarters of Nikon is in Japan, obviously, but Nikon AM, for the first time in 110 years history of Nikon, formed a company headquartered outside of Japan, United States. It's in Belmont, California. Our main operation is in Long Beach, where basically my office is. We built a 90,000 square foot facility in Long Beach, California, and housed one of our basically largest fleet of large format laser powder bed fusion. We acquired Nikon SLM Solution, which Matthias said that I'm not representing Nikon SLM Solution, I'm not representing Nikon AM Synergy, I'm not representing Nikon Organic, I'm not representing Nikon Corp, I'm representing Nikon AM. Okay, so we'll talk about like potentially what kind of business model we built, but we acquired Nikon SLM Solution about 3 years ago, one of the award leader in making laser powder bed fusion machines. Now our focus is really to make these large format laser powder bed fusion machines at a scale and helping industry to adopt those. Okay, so a wonderful talk, especially from my colleague at 3T. So when we are developing our business case, And it's very critical. When you're developing your business case for additive manufacturing, you must balance your economy equation. Otherwise, you will never be able actually to have a right argument that why I should do this with additive manufacturing. I'm not saying cost, I'm saying economy equation. The economy equation is different to cost. So there's so many other considerations when you're actually balancing your economy equation other than cost. It's like lead time, accessibility, maybe security, a supply chain issue. You have to consider all those tangibles and non-tangibles when you're building your economy equation. If it is not balanced, because additive is cool, because additive is a nice, interesting technology, it will not be adopted. Now, when we look at the ecosystem for industrialization, the first thing that we have to look at it is the value stream of qualified AM part manufacturing. At the end of the day, we will be successful as machine manufacturers, the CM successful as the contract manufacturers when we make quality parts at a scale and we can sell it. So it's kind of a different but similar explanation of what it goes to AM, the ecosystem of making high quality part, and the cost associated to each of the steps. So you usually start with an ideation. This is really very low cost. We have a great idea. We look at some parts, good. We can make this with additive. We spend a lot of time in the engineered solution. This is really important, and more money you spend here, down the road, you will see the benefit. This is where you basically start to looking, do I have a right part? Do I have a right business case? What kind of process should I use? Do I have a right suppliers? Is this a right material? Do I have right PCDs, specs? Do I have right ecosystem of post-processing lined up? Those all go to the engineered solution. Once you're done with this, the additive manufacturing, the printing part is not really expensive. It's actually easy. This is kind of the easiest part, is to making a part in a machine. Once you're done, I think the most expensive processes starts, and that's your post-processing, that's your lab services, a lot of metallurgical analysis. I'm a metallurgist. As metallurgists, we love to make coupons and break coupons. And if you look, how many coupons over the past 15 years we made and break, it's probably hundreds of millions of dollars spent in just metal, making these coupons and break these coupons. And then you get into data analytics. With AI, data analytics these days, pretty quick, fast, not really expensive. Then we go to inspection. And depending on what kind of inspection tool you're using, which you designed in your engineered solution step, it might be expensive, it might be actually fast, it might be not that expensive. But many of the aviation, commercial aviation, even some aerospace part, you still need to do XCT or some sort of X-ray, basically imaging. And many of those are very expensive, right? So that might be very expensive. And then if you have to go through a certification process, FAA, FDA, NASA, NAVIR, NAVSE, depending on who's your certifying body, then there is a process and cost associated to that. So this can be looked at in different way. Now this is an ecosystem of qualification and certification. And this is where all these steps, I think, in previous talk, you saw that, all those breakdowns of what is going to actually associated to the overall cost of the part, and what needs to be in place. So we will be able to successfully say that we scale additive manufacturing at the level that we want, not just making one part, two part, 100 part, but thousands and thousands of parts. We need to have the engineered solution capabilities. And what we're using a lot of modeling and simulation tools. We should not be shy to using those tools. These are really, really effective with all the computer capacities that we have, with all these tools that are out there. These are really helping us to reduce the cost of making high quality parts. Additive manufacturing, obviously using our machines, the post-processing from the depowdering, removing the supporter structure, cutting the parts from the build plate, heat treatments, HIP, maybe sometimes, few steps of heat treatment. These are all associated with the cost, and then testing, validation. Metrology, we are basically, again, lucky to have Nikon metrology, all the metrology, CMMs and X-rays, within our ecosystem, and we're using those, and then getting to quality and certification. Okay, so please remember this. These are really important. When we are talking about scaling additive manufacturing, you have to be able to scale all these steps, otherwise you will not be successful. Just touch point on our differentiating technology. We're talking about these large format AM systems, NXG and NXGE, or NXG 12 laser 600 and NXG 600E. This is kind of our flagship laser powder bed fusion systems that's being adopted with pretty significant rate these days, especially for aerospace and defense industries. So you can see some of the examples of the parts, the impeller for submarines or the aircraft pylon that you can make with these 600 by 600 by 600 machine, or 600 by 600 by 1,500 millimeter machines with 12 1 kilowatt lasers. One of the backbone of our Nikon AM solution for our customer is material data. A lot of things that we're doing is data-driven for our process qualification, helping our customers to adopt these technologies faster and much cheaper. We have a lot of data within our Nikon AM ecosystem. Every machine that actually goes through the process of releasing to customers, we're making a lot of coupons. Still, we have to make a lot of coupons, although we want to stay away from that, and I'll have in a slide to talk about this. Although I don't have much time, I'm looking at the clock right now. So we're making a lot of coupons, and then everything is like data-driven based on data. And we realize the importance of building materials testing within the facility that makes high-quality parts. So we built the A to Z material capability testing, from testing the powder all the way to look at the parts with XCT. Okay, so there's like nearly 30–40% of you are from academia. I have to put some ideas for you guys to think about, that how academia can help accelerating the adoption of additive manufacturing at the scale. So I mentioned about the challenges that we are dealing with, the costs associated to qualification, in general, introducing new materials. We had a small chat here. I don't want to introduce a lot more materials. Every new materials that you're introducing, meaning that you have to think about a lot of things, including the data, the sourcing, the quality. If we can somehow all together agree and work with few materials, at least for now, I think we'll see a much better payoff. But to just go through the challenges, today we have a very time-consuming and slow processes for the qualification. It's very cost-intensive, very expensive. The alloys and materials that usually introduced are not really AM-friendly. We're using old atomization technologies. There's some level of platform dependency and lack of standardization. And for that, we have a solution where we think that there are opportunities, and I'd like you guys to think about that as well, getting into more smart DOEs, using in-situ monitoring, using more and more smartly the non-destructive testing, novel atomization technologies. And if I combine all these together, we're talking about bringing ICME at a scale, integrated computational materials engineering. A couple of examples, we're heavily working on a material called CP1. It's the material that Constellium, aluminum manufacturing company, is basically they invented the material, and now they're making the powder. So this alloy gives us a very unique capability in terms of processability, as well as a high thermal and electrical conductivity close to pure aluminum. So you get the 6061 T6 properties with the conductivity of pure aluminum. And this is the material that we see a lot of our customers are now trying to adopt, especially in defense and aerospace, for thermal management applications. And we have invested a lot, in past few years to bring this material in the United States, qualified in different platforms. And we have some government funding actually right now to expand this activity. Another area that I would like, and I think Singapore can do a lot, universities in Singapore can contribute, is in situ monitoring. If you look at why in situ monitoring, some of these parts that we are making, 1.5 meter, 1 meter, it may take, in a slower machines, 20, 30 days, in our faster machines, 7, 8 days. I like to know if there is an imperfection, if there is a defect, if I'm going to basically reject a part on day 2 rather than day 21 when the print is finished, or after basically spending a lot of money on XCT and other type of inspection. So there is a very good use case and driving force for in situ monitoring in terms of quality assurance, in terms of rapid toolpath development, in terms of early build failure detection. We actually spent a good amount of resources and energy in building our own in situ monitoring. There's 2 ways of looking at Nikon, basically in situ monitoring today. One is looking at the surface, topography of the surface with the fringed or structured light, that we can understand the topography of the surface before and after recoding, and then looking at the multiple and measure the temperature of the multiple. For measuring the temperature of the multiple, you can't just use the one wavelength, so we built a proprietary tool that we can actually look at 2 wavelengths and measure the actual temperature, so we can see the actual size of the multiple. And the question is, how do we basically correlate all these data into the quality and into making a good part with the balanced economy equation? This is my last slide. This is another area that you can work. And we just recently published a paper around this, how to use high throughput material testing to lower the testing cost. This is the profilometry-based indentation plastometry. It's called PIP or PIP. And there's a company, PLX, startup out of the Cambridge University. We're working closely with them with all the activities that we did and they did. Now, this process is registered as, I forget the number, but it's an ASTM standard for this process. And we are basically going to expand our relationship with them and do some, not only room temperature, but also high temperature mechanical testing with this. So the good thing here is, very quickly with just one indentation, you can read the yield and UTS. And this is very good for process optimization, for the quality assurance, rather than making these tensile coupons and testing and spend a lot of money there. Let me stop here. I hope that I could basically explain a little bit about Nikon AM ecosystem. We are basically a partner for our customers with the holistic and kind of an end-to-end solution. Basically, again, from the engineer solution all the way to the qualification. And if you need more information, probably a few of my colleagues from Nikon SLM Solution are here, or you can actually reach out to me and we can have further discussion. Looking forward to discussing in the panel. Thank you.
Thank you very much. So, of course, everybody, we'd like to invite one more speaker up before we proceed on to the panel discussion. And he has driven the first application of 3D printing technology in the new industry and contributing to his company's breakthrough growth in Shenzhen. Could you please put your hands together to welcome Mr. Vincent Young, General Manager, BLT Shenzhen.
Well, hello. Good morning, everybody. Thank you, Namik, for the invitation so that BLT is in Singapore. Well, we are highly interested in exploring our next steps of potential collaboration in Singapore, hence I'm here. Also, at the same time, we will be happy to share a little bit about who we are, what we've done, and like all the other speakers. I'm actually very glad that we are looking at the same problems nowadays instead of, just everybody is shooting at different things. So collectively, I'm sure that over the next few years, we'll be able to help additive manufacturing industry, to achieve a little bit more than what it is today. Well, who is BLT? Instead of those numbers, I will tell a couple of stories. Bright Laser Technologies is a company that started its research back in 1995 in university. So we were actually in a research group of metal solidification. So over there, obviously, there are a lot of other traditional solidification methods, and then all of a sudden you have ideas on can we not spatially solidify materials by controlling them, and then using, for example, a heat source to melt them, and then move the heat away so that you solidify them. So these crazy ideas, when later it's been named additive manufacturing or 3D printing, were researched over there in 1995 back then. So from 1995 to 2011, there was our sort of commercialization or research stage. At 2011, we were actually asked to set up a company because we were making the wing structure, the wing supporting structure that connects the wing to the main body for a commercially flyable plane for COMAC at the time. So they had a couple of options. Obviously, the traditional one being the forging, and then 3D printing was later chosen because there were extremely tight timelines, and also because we were promising that we were able to deliver it with DMD. And then they asked us to step out of university, quit professor jobs basically, and then start to form a company afterwards. So our founder and CEO actually quit his job as a professor in university. Not saying that the professors here should do, but he quit his job and then started BLT. So from then on, we grew quite significantly. We at the very beginning was actually a enabler of applications, if you want. So we would come and promote technologies. So look, 3D printing is great, like everybody is doing. How can I solve your problem? What's your problem? So we're trying to use 3D printing to solve their problem. And then obviously at the very beginning, you would only be delivering parts, right? Because nobody is going to just buy a machine from the right off. So we delivered parts, and from delivering parts, people are asking, where did you print these parts? I said, we said with BLT machines, with our own machines, and then they asked, do you sell them? Yes. So we started selling machines, and after the machines are being installed, they ask, where did you get your powder? From BLT, from ourselves. Do you sell them? Yes. So we became, from a part printing services bureau, became a metal printer manufacturer, and then later included our competence in powder as well. So we grew in this way slowly and slowly, and we went public, obviously in 2011. Is now the most valuable additive manufacturing company in the world. We have a printer base of more than 1,000 printers in Xi'an actually. And then these are the 4 main business units. I'll go through them. Small systems, big systems, but in general, they're basically just for different industries. Overall, we've delivered more than 2,400 machines over the world, with more than 40 of our customers actually doesn't buy machines, they buy plants. So meaning that a line of 10, 20, and then you go and design the line for them, even the pipings, all the auxiliaries. The goal is that they can start manufacturing on just immediately after installation. Because we also is a powder supplier, so we have 2,400 tons of powder that's being sold to customers in more than 10 countries, and there's an annual capacity of 1,000 tons of powders as well. What's actually might be quite interesting that fits today's topic is that overall we have already produced 15 million parts. Yes, you heard it right. So 15 million. Obviously there is a growth of additive manufacturing in real landscape of manufacturing over the last few years. So that number actually increased drastically over the last few years, with more than 3 industries that's actually turning out more than 1 million parts a year. One specific industry that is more than 10 million parts a year. So maybe also look at a little bit our approach. Like the other speaker has said, for us what's really, really important is that BLT as a company that helps to enable additive manufacturing to be in the mainstream of manufacturing. So we want to see additive manufacturing being the method that's being used to produce everything. And with that, I think we are helping the industry, and obviously with our solution, that the industry can then decide whether they want to pick on the solution to do the same as well. So it's a very open business model in the company, but what we're doing is that we're doing a few more steps to try to ensure the results are right. So for us, application development is like cooking. You have all the ingredients on the left. You have your broccolis, your meat, your salt, your whatever that you want to put in. Those are machines, materials, technologies, support generation, simulation. But then they need to come together to become a dish. And that dish needs to be recognized by people to say that, oh, this maybe is a good dish. And that's only the very, very beginning, actually. That one good dish is the first step for you to set up a Michelin restaurant, because you need to be able to turn that dish, you need to be able to basically validate it, to say that, okay, maybe I can do 15 of those dishes a day, or 100 of those dishes a day, and then the last bit is the hard bit. I like the what Matthias has said, to make 3D printing boring, that you do it day in and day out, without people even noticing that you are using a new technology. So starting from identification, we cut out 97% of the projects, not because they are not suitable, but because we need to focus our efforts on delivering value, so that step by step we can make more people believe in the additive manufacturing industry. And then you need a lot of capabilities. So within BLT, all the way from material, from alloying, powder making, process engineering, software and algos, to the machines, peripheral machines, MES and automation, and also new application development, design engineering. All of that are each and every individual teams, and some even departments that supports our customer in every single aspect of those development. Because without that, you wouldn't be able to give them a total solution or a one-stop shop. And after we've done that, from a business model point of view, we're actually quite relaxed, because it doesn't really matter for us whether people want to use the machines or the powders to manufacture those parts, just as we are able to do them, or people want to use us as a contract manufacturing business. For that reason, actually, our revenue split over the last 10 years has always been 50-50. I mean, 50, 50, 55, 45, stuff like this. So a lot of people actually are utilizing this, like the openness of the business model, to maybe let us do the experimentation, let us fix all the variables, and then they will just go on and buy the machines and do the volume themselves. So we can give a lot of examples, but a real life example of a real huge volume application is actually very difficult. As you guys have been in these activities, the amount of $1 million they make you sign their confidentiality agreement. So most of the time you cannot say nothing. And luckily we have Oppo that I think had announced their hinge probably half a year ago, and they actually had cited BLT because we've been in development with them. So this is the one case that I can talk about. It's actually a very cool case. So first of all, it's what does it do? It's the thing that underneath your foldable phone that supports the screen while it's open, so that your screen looks flat. Without that thing, your screen while it's open will look very, very curly. So this has been a key component for the user experience with with these foldable phones. Well, it wasn't actually, I mean, before additive manufacturing was doing it, it was also there. It existed. It was using carbon fiber. The reason why carbon fiber doesn't fit the bill anymore is because they've made these phones so thin, 8.8 millimeters when folded up, actually 8.7 or 8.8 millimeters when folded up. So when you open up, the one side of the phone is about 4.2 to 4.3 millimeters. And with that, titanium, carbon fiber needs to go down to 0.2 millimeters. And when carbon fiber goes down to 0.2 millimeters, there is no stiffness. Without stiffness, you don't hold the screen. Without holding the screen, your screen looks bad. So hence, you need a solution to be able to do that. Therefore, they came to 3D printing. They came to titanium. And then they looked at titanium as the 3D printing as the best option. And obviously, they went to look at everything around every possible process around the world. But the end conclusion is that 3D printed titanium, especially with the technology of LPBF, is able to give them material property, is able to give them deformation control, is able to give them tolerance control, and more importantly, is able to give them the stiffness that they want across all their phones. So they chose 3D printing. We have been doing quite a bit of work with them on enabling this, and it was crazy. So if you look at it, I mean, hitting those tolerances, for me, I think it's okay. I mean, you have ways of hitting, obviously, those tolerances, but it's about hitting those tolerances 3 million times. And try that. That's the most difficult bit. So with us, we're really lucky to be able to collect those amount of data, and so that we have fresh and new insights on how this industry should go forward. Yeah, and then the first 1 million needs to be delivered within 10 weeks. That's that's also a trick. I mean, obviously, I think, if I'm not wrong, these prints are about 2.5 days for around about 1,000 of them. So you need probably, I think it was 50 to 60 or 70 machines that you need to print together, and you need to ramp them up, you need to qualify them, you need to validate them, all that sort of stuff needs to happen within the first few weeks. And then, you start producing these things every single day, and there needs to be no problem. Yeah. So overall, these are the cycles of what we call mass production phases, all the way from concepts to protos, and you go from protos to your engineering validation, design validation, and then you start ramping, and after ramping, you do your sustaining. So it's actually not just 3D printing. It's engineering, but 3D printing happens to be the technology that we are using to engineer new products. And then, you have timelines, you have processes predefined, and then you have readiness that you need to map out. And it's not just the readiness, actually, of 3D printers. It's the readiness of everything, yeah? Method, machine, material, manpower, environment, every single one bit, even that carbon fiber exhaust pipe that you may be actually letting carbon fiber out to the air. If that's not qualified to the regulations, you cannot ramp. So I mean, there are stuff that like that's way more than machines. And then you have the life cycles of this, and then you have to simulate what the gentleman from 3D has said is that people need backups. And that's especially true because people are never trusting additive manufacturing at the very beginning. They don't trust it. They want to design adjacent technology that's also able to do it. But if they don't, like this hinge, they freak out. They make you do scenario 1, 2, 3, 4, 5, 6, 7, 8, so that in the worst event, when you have an earthquake, that's your factory and all when you have a earthquake, you have a flood, you have everything together that destroyed your factory. You still have another factory that will make sure that the product launch on time. So that's the kind of stuff that we're made to do, so that people get comfort to say that, let's go, we will ramp with additive manufacturing 100%. And then obviously, while operating, you have all these, MES systems that manages everything, that tracks everything, that learns from the previous failures, so that we know what to do afterwards. Speaking of future innovations, I guess most gentlemen has already mentioned everything. I would just touch upon the importance of being able to predict accurately and being able to feel or sense what's exactly happening during the print, and being able to be assured that we're executing whatever the command we want to execute to the full extent. And we need that cycle to complete, and then we need to add data analytics to it, so that we are able to predict, we're able to sense, we're able to potentially correct, but not necessarily correct, but we just need to realize, and afterwards we need to analyze to see what kind of things are not being done correctly. And if we have those cycles done in the next few years with additive manufacturing, I think this will be the easiest technology to manufacture ever. With that, I conclude my presentation. Thank you very much.
Thank you very much. So with that, everybody, we will be proceeding on to the panel discussion. All right. So, of course, coming up on stage, we have the various gentlemen who have just spoken earlier. So, our moderator for this session, he's none other than Mr. Matthias Schmidtler, Managing Partner of AM Power. Panelists include Mr. Alex Monino, Senior Vice President and General Manager, HP Additive Manufacturing Solutions. Mr. Eddie Andrews, Commercial Director, 3T Additive Manufacturing. Dr. Birang Pogangji, Vice President of Technology, Nikon Advanced Manufacturing Inc., and Mr. Vincent Young, General Manager of BLT Shenzhen. So, gentlemen, please be seated accordingly to the photographs. And of course, together they will be tackling, are we really ready to manufacture differently? So I'll leave you in their good hands.
All right. Thank you, gentlemen, for joining for the panel discussion. I want to open the question with scaling additive manufacturing. We've just seen a very impressive example of scaling, but we see different industries adopting additive manufacturing. And while we look at consumer industries, we quickly see millions of parts in the market, but we serve with additive manufacturing many different industry verticals. I want to start with a question of what scaling actually means to all of you, because we see many different applications in the market, in healthcare, industrial, and aerospace. We talked about ASML. It's certainly not millions of ASML machines out there. So what does scaling means to each of you? I just want to address that maybe to each of you, from your perspective as supplying parts or supplying machines into the market, the scaling actually means, and what's the impact of it? Alex, you want to start maybe?
Yeah, so I'll give it, I'll start. So for me, scaling means that it's not a niche anymore. It's not a use case that it becomes the norm. It kind of gets boring, as you were saying, in a way, right? And it becomes mainstream. I think there is different applications, as you said, that scaling will mean that you print 3 parts a year, and that means scaling. There is others that you print millions. So I wouldn't, and I think it's different by segment. But I think we're still at the very beginning of the adoption cycle of this technology as manufacturing. I really like the fact that, and I really believe that when they ask me what the key competitor is, for me, I'm saying it's the inertia of the engineers designing the same. I think you brought up the fact that, they need a plan B, so they're not fully designing for additive in case additive doesn't work. And I think, once we break those barriers, we'll start scaling, and then that will bring the revenues, the numbers that, we are looking for.
Nick, you bring the aerospace perspective. What does scaling actually means in aerospace?
So, I don't think it's just exclusive to aerospace. To me, scaling is just about getting ready for production. It's being able to invest in the capacity, in the capability to achieve the quality that each industry sector needs. I don't think it's anything. I mean, we can talk about quantities of part numbers, and thanks, Vincent, for making my 12,000 parts look a little bit small after seeing millions of parts on the slide. But I don't think the quantity of parts actually determines the magnitude of the scale. I think it's just about the investment that's needed to scale.
Vincent, I'm going to jump to you because it directly refers to, and you're shaking your head. I mean, hundreds of aerospace parts versus millions of consumer parts. Is there a difference in the end? Or, I mean, you have experience with aerospace as well, BLT.
I mean, numbers sometimes trick people, you know. What I forgot to mention is those hinges are 1.3 grams per piece. So with hundreds of kilos of the aerospace parts, I mean, that's also scaling, I'm sure. For me, I mean, obviously there's one side of the scaling that's purely on, you know, increasing your capex. That's the most obvious one, and being able to still operate at the same amount of same quality, same attention to detail after you have a huge amount of influx of capex and a human being, for example, like new laborers are being trained for 3 weeks and they need to execute exactly the same. That's in itself a very a difficult thing. What's also getting interesting, you know, over the last few years is that once you get people excited for, take consumer electronics, for example, if we got Oppo excited and all of a sudden that company has 50,000 people swamp on us of a company that's only 3,600 people. So we couldn't even man-mark them, let alone handling all their projects. So scaling from an engineering point of view has also been a huge challenge with additive manufacturing, and it's going to be an even bigger challenge to come going forward, I think.
Yeah. Barang, you mentioned aerospace sector, defense sector, large parts. Is large parts also scaling for you, or? I mean, can you imagine, Vincent said 60 machines just for one part. Is there going to be 60 NXGs for one application?
Yeah, so I think scaling is really depending on what industry you are really talking about. But the first step in the scaling is, I have the right application, I did all the necessary analysis, and I'm convinced, right? Convinced that's the inertia of all the engineers and everyone that needs to actually sign it off. I'm convinced that I can make these parts at whatever number. Is it like 100 per year? Is it 100,000 per year or 100 million per year, right? I can make those because I have studied that there is an ecosystem of part manufacturers, post-processing, inspection, and I have a right business case. So when it comes to aerospace and defense, obviously, you know, we are not talking about millions of parts. That's not that business. But now we are seeing more and more, because our machines are obviously larger and more productive, and we learned by actually doing a lot of other type of work. So I think what you're mentioning, hitting those tolerances in titanium, Ti64, for a phone hinge, right, can actually enable you to make those tolerances for, you know, aerospace application as well. This is an interesting thing in additive manufacturing, that, you know, we have a multi-purpose machines that whatever we're going to make with those machines will enable us. You mentioned about now you are very much fortunate to have millions of data points because you build something, you know, million times, right? So it means that now you are way more educated to use that very knowledge to make very complex aerospace and defense part with the very same material, right? So an example that I think enables us to scale is, imagine that you have a 1 meter part and you have a 4 laser and you want to make these 1 meter parts. And we have example of those that we did a study. It would take 43 days to make that part. Okay, so imagine what can happen in that 43 days. A gas fluctuation, electricity fluctuation, for whatever reason, oxygen sensor may go bad, anything could happen. And you have to restart. So when I'm looking at this and saying that, yes, I can make this, but probably will not be scalable. But now I have a technology that with 12 laser, I can make this probably in a week, right? And I have good controls in place, so it will be scalable. Then the question is, where are those machines? How many of those are available? Yes, I mean, I think we are all at the point that with the right applications, we can scale.
Good point. I want to also ask the audience to propose some questions. We have the Slido app. I think you have some QR code on your desk, on your tables. There's a couple of questions already coming in. Please go ahead and like them, push them up, or post some other questions. I want to continue the discussion with going into a very specific field of scaling, which I think is very interesting, because from the beginning of additive manufacturing, a lot of emphasis was being put on customization, because additive for the first time actually enables you, next to many other advantages, but one major advantage is you can produce parts digitally and you don't need tooling. So if you have a tool-free production, you can customize, you can mass customize at some point. I think especially in the polymer section, that's one of the major advantages, why we talk a lot in metals about applications that we want to produce the same way 100 times or 1,000,000 times, where we're probably trying not to customize anything and we're trying to freeze the process. In polymer, it's a totally different story, Alex, isn't it, about customization?
Yeah, it is, and it's kind of the holy grail and somehow the standard today. So if you look at all the medical applications, at the end it's mass customization, right? We're doing, hundreds of thousands of insoles or millions. You're doing aligners. There is the whole customization workflow, and that's enabled by the medical workflow. I think the challenge is going to be, bring that beyond medical, and can you bring in mainstream into consumer goods, right? I think there is one technology that has changed, which is AI. Before, in all those workflows, to design a personalized tool, imagine that you want to personalize a keychain, right? And you want to before, it took hours to design that keychain, which made it not viable economically, because you had to put 2-3 hours of design just to do keychains. Imagine that we wanted to do keychains for this event, right? Personalized with the names. It was not viable. Now with AI, that's just very, very viable, right? So I think it might open AI and the, enabling design at a very low cost. It might open a new set of use cases for personalized merchandising, et cetera, that might be viable. And then the other thing is other parts of the body, like shoes, et cetera. When will they get those personalized? And I think that's where medical will take. I think we'll see it right now. We're seeing products that are only medical. We'll start seeing, some shoes that have, some personalization, starting for some medical applications, and that eventually will scale into mass.
So towards the metal fraction sitting here, how is it about metal? I mean, we've seen some applications of not mass customization, but of customizations in medical and the implant area, some individual reverse implant, for example. But do you see other applications in metal where something of customization plays a role, or is every focus right now on actual serial products of the same kind of product 100 million times?
So I would still say the focus is on production and doing the same thing over and over again.
Well, it's both production, isn't it?
Sorry, yeah. So I would say standardized production, doing the same thing over and over again. But I do think the applications where you need to tweak and have a small number of parts that just changes in variation over and over again. Medical's the great example of this. But when we go to additive is not the only manufacturing process. It very rarely creates a finished part in additive. You've still got to do all of the finishing processes. So mass customization, you still have to mass customize your CNC machining programs. And there's no easy way to do that. You've still got to reprogram. So it's not as agile. The mass customization isn't as agile as we think after we've got past the additive process itself. I still think there's a good use case for mass customization. I just don't think it's the only narrative that that we should be pushing in the industry.
Different opinion, Parang?
No, I think, again, like probably in metal, we see less mass customization, or, depending on how you define customization. If you think about a bucket of application, let's say, the bucket of application is blades, right? Just imagine. I'm not saying that we are printing all the blades, but let's say blades is a bucket of applications. We can customize it depending on, which engine, which stage. This is custom. This is one way of looking at customization and additive manufacturing, because it's digital manufacturing. We start with a digital file. You can very easily tweak that file, and you can call it I've customized it. But I think at least our understanding in AM community from the customization is, okay, I want to make an implant. This is customized to that patient or that animal or that specific use case. So I'm able to make millions of implants, but at the same time, each of these implants are different because each design, or there's a curvature, or there's like something is different. You can look at it both ways. Additive manufacturing provides us that capability. If we have a qualified process, qualified material, and go through everything, and it probably needs a little bit of a change. I'm not 100% sure how FDA will look at it in terms of like customization when you do some design changes, minor or major. But yeah, I think we can do that. Should we do that? Again, I always go back to, do I have a right economy equation? Do I have a right business case? Why should I do this?
Vincent, how about consumer electronics or consumer industry? You have a closer look.
Yeah, well, I agree with what the gentleman has said. I think whether it's necessary is a question that needs to be answered. But from my point of view, I think somehow it needs to be enabled going forward in metal. Maybe one small example that we ran into is that you have to laser barcode every single one of your parts. That has to contain the information of where that is, which batch it is, which powder it is, who handled it at each and every single station, all the way until that is laser barcoded. So I mean that's a customization. That's a customization, and that, in my opinion, should be enabled. Just as there is one project that I had a discussion with 10 years ago in the UK on engines, where you print engines. A lot of them are as printed, but you leave a certain space with a certain volume that say that this area is customizable, so that every bit of information that you have is MES pushed, slicer enabled, on that specific volume, and then you have a change of slicing path, which gives you a certain different logo. So what I'm saying is that it might actually be very interesting, because we're talking about a technology which is capable of doing this, to actually just do it without the intervention of laser barcoding afterwards, because then it's doubling the work, right? Yeah. You first print the whole thing, and then you laser barcode out something which costs extra money. So yeah, that's my opinion on this.
So there's one question in the audience that I found interesting. There's a question that says, what's one bold change you think the industry must make in the next 5 years to truly move forward? It's an interesting point, because I think I put in this word of boring before, and I think everything you guys talk about is not really innovation, right? It's not really about moving a technology to the next level, or increasing speed by 100 times, or introducing a new type of 3D printing technology. It's actually about using what we have today as a technology basis and just incrementally improve, include it into a more complex process chain, etc. But are there maybe things that you're generally missing in the process chain we have today, in the ecosystem today, or other things maybe you're working on, or maybe others are working on, that you find interesting? You mentioned AI. Are there things left and right of the 3D printing process that we need to incorporate or utilize to bring AM to the next level and actually do grow the way we all want it to grow?
So maybe I'll go to the very left of the process, and again, I think one of the key barriers that is preventing AME adoption at scale is people continue designing the regular way they've been designing, right? With the constraints of the processes that exist today and kind of the constraints of the process of Plan B. So I think one thing, obviously, as we gain credibility, we will show that people that Plan A is good enough and they can rely on it. I think, having tools that help those engineers to really redesign those parts into 3D and kind of those constraints with the use of AI, I think at a mass would help us, to get, more funnel from the upstream. That's I think, because honestly, I think that's we're kind of pushing a rope in that sense. And in a way, we need to find all of those engineers that are graduating and are joining companies to be able to change the mindset. I do have an example. We have one customer that's a tractor company. And we have, in one of their tractor models, they have more than 150 parts that are 3D printed in production. Joysticks, all of the parts. So then we met with the C-suite of the tractor company. It's like, okay, you have one model that's 3D printed, but you have another 20 SKUs that have no 3D printed parts. And their answer was, the group of engineers that's leading this particular model, they're motivated, they're forward-looking, they're doing it. There is no reason, no fundamental reason why all the other tractors could not have it, right? They found the economics, they found the business case to move all those parts to 3D. So, you bring that at scale, and I think that's one limitation of the industry.
Brang, you want to add something?
Yeah, so I think it's an interesting question. It says truly moving forward. So I don't know who asked this question. You think that the industry or AM is not industry, but AM technology is not truly moving forward? What is that truly moving forward should be? Just look at, what we did over the past 15 years. And I'm just saying 15 years because I don't want to go, people can claim that, it's 50 years old, 30 years old, whatever number. So look at the casting industry. And casting is an industry. So we have like more than 1,000 years experience, and that was the quality of the casting parts that we would see. And with AM, with around 15 years, we make way higher quality parts and components in casting. So what exactly we are expecting too much, and I think we have to expect too much. We always need to set the bar high. But at the same time, we still look at, what in human history we have achieved in past 15 years, which is almost same or way better than, 1,000 years. Of course, we have computing capacity, design, much more educated. We have a drive. But look at this. But if and again, like one thing to change, there's always like these chicken and eggs, someone should cut it. But one thing to change is there should be no plan B. There should be only plan A. And plan A is using additive manufacturing. If you have the business cases, use cases, components, that there's no plan B, there's only one plan A. And I was in a meeting that CEO of GE Additive, who were behind the qualifying that very famous fuel nozzle, right? I'm a GE person, I came from GE. So he was in a meeting, said this, no plan B accepted. You make the plan A work. That's it. You make the plan A work. And plan A worked. And plan A is working for 1 million or, a few thousand or hundreds of thousand parts that we are making for the other industries. It's working. Yeah, I mean, just come on your Fridays to these type of things and let's push it all together. I think that helps us. We are truly moving forward.
So is it, if I take your idea, Alex, it's probably about the human factor. It's about design, right? It's about mentality to design for AM, to accept only plan A and accept the technology as it works. Do we maybe need to push that industry a little bit? I mean, right now everyone is still designing parts. The majority of companies are still designing parts with a Siemens and Autodesk or whatever tool. Are those still the right tools? Do we need to push those companies a little bit more, or do we actually need a complete new way of designing components in order to push the edge and bring companies to adopt more applications early on in the process, in the thought process of parts? And do we have the right software tools to actually design?
So I think if I answer the first bit of the question, then I agree with Alex. We still need to create a commodity around this, and it doesn't feel like we're in a commodity yet. Customers feel locked in. Whoever they select as the contract manufacturer, they still feel pretty locked in. So I would say it's that getting that critical mass of suppliers who are at that level that they can be convinced that we've got a competitive marketplace, they've got the capacity that's in the supply chain, they've got the plan A through to Z. Then I would say a lot of the customers that we've got who've had the early success cases, they've taken years to develop the first part, and they've sold it internally, and all of the management is absolutely convinced now that AM is the right thing to do for their business. They've seen the benefits. And then they go, come on then, let's push. And these engineers say, well, it was just a small team in the R&D unit who made this happen, and it took years. How do we accelerate that? Because the rest of the organization doesn't understand how to design for additive. We don't even understand how to select the right parts. Vincent, you had your chart here that said that 98% of the parts that you see, you filter out. You know, these are the tools that they're starting to come into the industry. I'm starting to see them come in a little bit now to do that filter of what's a good part to go after. And then there's the tools that how you're going to then design it, and then there's a cultural transformation around designing for additive. In fact, designing agnostically, because I don't think we should just start pushing design for additive on everyone in every organization. It should just be something that you can do if it's appropriate for that part, but it shouldn't be something that we're just trying to push them like lemmings to do. Then your last point on where's the space where there's software platforms that don't exist that should be. Interestingly, I'm here with a colleague from another company who's developed the first piece of software that connects the CAD to the simulation. And so what he's done, and actually I was gobsmacked when I saw this, because you've got all of the CAD software providers, and you've got all the CAE software providers, but these parts are getting way more complex, and so the simulation is now not taking just weeks or days, it's taking months and months and months, and just tools like that operate in the center that can accelerate the simulation of design is going to really help that design process. So tools like that, I think, is probably what I see as the biggest gap in the industry.
Anyone wants to add something? Rang?
Yeah, I agree. Again, not everything needs to be made by additive, and not everything needs to be redesigned. But I think collectively we are not necessarily using the capability of redesigning and designing for additive manufacturing and make additive more viable solution. I think that's what we probably try to say, that, you know, if we use all the tools and, you know, that we have in our toolbox, we will make additive manufacturing a more viable solution for broader number of the parts. And if we're using this, well, we see that, you know, more adoption if we don't use it. But I think fundamentally, again, AM as a technology should reside at the high or top of the list of the engineers when they start thinking about designing. And maybe it is not today for every engineers in every organization, but I think probably in next 10 years, we'll see that it's probably, you know, new engineers will jump into additive manufacturing. Can we 3D print this? And if they say that, no, you know, it doesn't make sense or whatever, then they go to the next, you know, next and next. I think that's probably what we want to say.
Vincent, you mentioned that you're now being exposed to more departments within Oppo to actually think additive and consider it as a manufacturing technology. Do you also see that as kind of a lightning house project, a beacon project for other consumer electronic companies? Are they watching what those companies are doing, how they're manufacturing? Or do you see more traction also coming from those other cell phone, laptop, whatever company?
Yeah, like I said, there are extremely strict confidentiality agreements that's being put in place for us to basically say nothing. So Oppo is just an example that I can use to elaborate the mindset or the movement of certain industries, into looking at 3D printing. Coming to what the gentleman has said, I think what's actually quite interesting in that industry is that they have a feeling that they have to use it. If not, their product will not be as competitive anymore. With that feeling, though, there are obviously two sides of the coin that you can look at. That one feeling is that everybody is thinking about, can I use additive manufacturing in the first round of their design thinking? That's good, but I have screws put in front of me to say that, can I print the screw? That's horrible. So I mean, so going forward, I see the point of trying to educate people so that they at least can choose the right thing. I also see the point that, hey, come on, we can print everything. I mean, somehow we have to find a certain balance, because we can't have all the modules coming to us and immediately expect a part returned to them in perfect quality in 3 days. Just simply, that's too much. So maybe they have to be able to down select. Maybe they have to understand better the value proposition. Maybe there needs to be a team inside their organization that sort of pre-filters that. Or maybe additive manufacturing needs to improve, speaking of the question, to be able to always deliver what people wanted. Because, I mean, at the end of the day, we're talking about design for additive manufacturing is because there are certain things that additive manufacturing is just not good at, right? So, can we be better in that? Maybe, as well, right? So then we don't need design for additive manufacturing anymore, right?
I want to switch a little bit to the drivers of scaling AM. We talked a little bit about medical applications. We talked about aerospace. We talked about consumer electronics. I think we touched the major areas of growth in AM. But I'm interested in other industry examples that you can name, maybe where you see in the next couple of years maybe a scaling driver in terms of certain applications or industry segments that are adopting. What do we not see yet, or what do you see in the market that the broad community might have missed over the past years, where you maybe see a chance that this can be the next application that's gonna drive AM?
So I might start maybe more from the polymer side. First is just a realization that this is an industry that's going to be driven application by application. So that's having the right solution for that application is going to be key. Having said that, I talked about drones. That's something that's really growing a lot, and that's a reality today. We believe that one of the potential next wave is humanoid robots. I think engineerings there are really taking advantage. That's where weight it's paramount, because at the end, when you take weight off, you can put that weight on the batteries and have it last longer. The lower the weight, the smaller the motors, the lower the cost. So it's just kind of a self-fulfilling prophecy. We have one example that's public that's called Ocado, which is not a humanoid robot, but in a way it's a robot for Ocado. Basically, it's like an Amazon type of in the UK. They have a huge warehouse where they have the goods, and basically you have a robot going on rails, picking up the goods and setting up your purchase, right? And they are 3D printing. This is a group of engineers in Sweden that then they went Bologna. They designed everything 3D, and they reduced weight down to 50%. And therefore, they reduce the whole system. They reduce the railings, the robot, everything, right? And that's an example that will happen, I think, in humanoid robots.
Makes sense. Anything from the metal side that you see as applications beyond aerospace?
Honestly, I think everything, we're looking at a time frame in the next couple of years. I think we're seeing everything that will emerge and go bigger. But it's already in our businesses. We're seeing it in RFQs. You probably see it. You develop it on the machines now. You've seen this type of stuff that works. And our insights will probably be different, because I would say you guys have probably asked for the more boundary pushing applications, because you're developing the machines and you're getting the customers who really want to challenge what you're doing. But I would say I would take it right back to the really boring stuff and say, we're expecting the growth in the short term to come from not parts that are designed for additive, not optimized for the process, but just addressing an immediate customer need, whether it's a quality issue in the supply chain, a costing exercise, or just lead time reductions. And the casting is the perfect example of that. And I think those are the applications that are really going to ramp over the next 2 to 5 years.
Yeah, I think that's pretty close to what I'm thinking. 10 years ago, when we were trying to sell, why additive manufacturing, we were always talking about the potential for lightweighting, the potential for combining so many parts, so simplifying the supply chain, or some of the joint or welding removal, things like that. And then we always had a bucket for functionality. So the future systems, whether it is cell phones, which become foldable, or medical devices or weapon systems, these systems have different needs. And to answer those needs, you need probably additive manufacturing. And I think an application that I encourage everyone to think about this, or a bucket of an application that additive manufacturing will shine, is thermal management. So we are generating, for whatever reason, adding more electronics, using electricity more and more, electrical cars or vehicles or drones, or you just name it. So we are generating more heat, and we have to remove this heat. And we need better heat removal tools. So that's why I call it thermal management. I don't necessarily call it heat exchangers, but heat exchangers is part of the thermal management. So we'll see a very large, I think, adoption. And additive manufacturing is shining because of, you can make very sophisticated structures that there is literally no plan B. There's only you can make it with additive, with metal. And that would be adopted. I think that's an area. There will be a lot of opportunity for implementing design, great modeling and simulation, making our processes better, and making it large or very small.
Vincent?
We're getting to the stage where many of the so-called there's no plan B applications that is popping up because of maybe engineers, they're young engineers who starts their own company and look at things. I have a client that's ingenious in what they're doing. They put they are in microsurgery business, where what they do is they try to minimize the sort of the head of the microsurgery the robot, so that it goes into access to a larger percentage of the body. And by doing that, you have to integrate sort of basically every function of that needs to stick out, needs to be able to rotate, needs to come out and cut something and grab something, all that in a diameter of 3 millimeters. By doing that, you access to like apparently 70% of the body. I don't know. So additive manufacturing becomes the plan. There are literally just no other plans where you can do this. And they are successfully in trials already. So that exemplifies, I think, what additive manufacturing can do. And it really, it's not a job that has a lot of revenue for us, but we had a lot of engineering hours that we were sitting with them day and night, thinking about how do we get rid of this bit of diameter, how do we get rid of that bit of thing. And then you have this bike industry, and all of a sudden somehow, everybody's having some sort of titanium printed something, on their bikes. I don't know why, but like we have more and more of these things that's coming. Robots are certainly one, as you said. Thermal management is another one. It's just interesting that 15 years ago, when I was at Birmingham TCT, I was explaining to a grandmother with a granddaughter on what 3D printing is, and now we're here, having lots and lots of application, actually, if you really look at it. Yeah.
There's one question that many people like, so I have to ask it. Eddie, you have to mention can you please mention the software firm that you referred to?
Yeah, it's a
people are very interested
it's a startup company from the UK called Voxshell. They're down at ITAP, so if you want to go and see them, they'll be there for the rest of today.
Hope everyone understands that. Okay. I want to ask one last question, maybe to each one of you. Remaining with applications, if you think back the past 12 months, let's say, and look beyond what you shared maybe in your presentations, what is an application that really made you excited about additive manufacturing and made you convinced that this market is going to scale, is going to grow? Maybe you can share one insight from the past applications you have seen at customers, and you are able to share something interesting beyond the presentations. Who's first?
I can go first because I'm not going to share the application specific, but I would say in past 12 months, what excites me and I think our team in Nikon AM is additive manufacturing is a tool become more and more evident as a potential to address some of the major challenges that we may face in next 2 to 5 years. Whether it is about security of the supply chain, whether it's about the type of the systems that we are introducing, the functionalities. So I think it's become more and more evident that we need to pay more attention, invest more, and make sure that additive manufacturing is not just a tool in a toolbox for some cool or maybe making bikes or some other type of things. People are really, really taking it serious, and it become a highly important technology. And I think this is global. It's not only like in Singapore or in the US or Europe or China. I think globally everyone understands that how important it is. And I think that excites us because we are seeing more and more successful use cases, not just from the application perspective, but how it impacts certain industries. So again, additive is not an industry. Additive is a technology. And it's very interesting to see that this technology become so critical and people are looking at it with very critical eye. So I think that helps because it brings more investment, it brings more people, and hopefully it will scale at the level that we expect. But remember, we came a long way in past 15, 20 years. We should always think about the way that we came and think about what else we can do.
Okay. Makes sense.
I've signed too many NDAs to talk about applications. But what I will say, and whether this is just a Europe thing or whether you're seeing it in China and the US as well, but it seems like the aerospace OEMs are now starting to engage with the supply chains in a more, we need to kind of start getting prepared now for what's coming. So we're starting to see that engagement now in Europe. And that was always touted as the biggest opportunity within additive. For the last 15 years, we've always been aerospace is coming, and the majority of these use cases are still within the OEMs. They're still manufacturing internally, whether it be GE or Rolls or Airbus. I know you've got the Airbus parts that you're doing. But I would say that's a real exception in the supply chain. But the engagement we've had in the last 12 months gives me a little bit of a glimmer that this is just starting to open up, and but they're not coming to all of the suppliers out there. They're coming to the ones that have already done the hard work to get into production, the vertical integrations, the working on the cost base, because they know that the ones who haven't got there, they're too risky to execute their strategies. But I would say that I would be expecting aerospace to become prominent within the supply chains in the next 2 to 3 years.
Alex?
Okay, so I'll share maybe not a very sexy application, but it's a use case that I think exemplifies, I think, what would open a little bit more the adoption. This is a pump customers in California, and they had a supply chain issue, and they ended adopting 3D. The parts that they used were much more expensive, so they would have never been able to go through procurement, etc. And only by using and justifying the end-to-end, right? So they were able to, that company was able to justify and then using AEM to design product faster, to build supply chain resiliency, and at the end, it made their overall process and their overall product much more efficiency, much more competitive. And it's one of the use cases because we typically talk about cost and et cetera. It's one of the use cases where really that customer built in the overall reasons and the overall benefits of additive end to end, right? And if more customers did that, and I think we're still kind of stuck between maybe just the engineers that design the product, that they want new capabilities, and then procurement that they want, right? And we're missing, a lot of departments there that would see a lot of benefits if maybe even the accounting of the companies would account for it differently.
Right.
There are too many applications that's exciting out there. I think maybe what I can share a little bit what I think after dealing with these people who basically in the end decides on what process to take on as their MP process, what's their selection criteria. I have a feeling that they are, obviously they are not as attached to additive manufacturing as us, so they actually don't care what technology is your part being made. It doesn't really matter to them. So as long as there is quality, you deliver even a second faster than the other technology, you have an advantage, and it has to be cost competitive to all those technologies that, like you said, existed maybe 1,000 years or 500 years. So that's the tricky bit at this moment, I think, with additive manufacturing. Sometimes I need to convince myself almost to forget that we are using such a cool technology, to not get too attached to the technology, to turn my head back and say that, look, this technology has to find a way to cost down. Otherwise, we cannot compete. So once you do that, and depending on different industries, you get to a certain threshold where application will just pop up. You don't need to go and find them anymore; they will pop up. So that's for me what I realized over the last few years.
Very good point. Thank you very much, gentlemen. It was great talking to you. I think we can continue the discussion endless, but unfortunately time is up. I think it's lunchtime too, so we don't want to hold you guys back anymore. Thanks again for your presentations, first of all, and thanks for joining this panel. And yeah, hope you all have a great lunch break. Thank you very much for
Thanks for
joining.
moderating.
Thank you very much. Gentlemen, could you step in front for your group photograph, please? And of course, everybody, we will be adjourning for lunch. Just before that, a quick check. If you could just kindly scan the QR codes at the back of your badge, you could provide us with your valuable feedback. Lunch is served outside. We'll appreciate your assistance to be back here by 12:40. That's 1240. Thank you very much. We'll see you later.